If you are building robotic foundation models right now, you know the absolute nightmare that is the embodiment gap.
Oh, yeah. It is a brutal problem to solve.
Right. So welcome to AI Paper Slop. This is our YouTube series where we summarize AI and tech papers for you. And today we're looking at a really wild paper out of UC Berkeley.
Yeah, do as I do. Dexterous manipulation data from everyday human videos.
Exactly. And let's just get straight to the core insight here. This paper essentially solves the human-to-robot translation problem for dexterous multi-fingered manipulation using purely observational monocular RGB video.
Which is huge, right? Because they are pulling 4D hand object trajectories out of just, noisy internet video and then mapping it directly onto physical robot hardware.
Right onto the hardware. So give us the technical TLDR. How are they doing this?
So the core technical contribution is this DO as IDO framework. It is a highly specialized two-part pipeline.
Okay, part one.
Part one is a 4D hand-object reconstruction process. They use a novel guided diffusion technique that actually repurposes SAM3D.
Wait, they use SAM3D to track objects through severe visual occlusion?
Yeah, exactly. And then part two is a dynamics-aware retargeting process. So here, they run an MPPI-style sampling-based optimization.
Mujoko warp.
Right, you got it. And they introduce these critical innovations like warm-up steps and random force perturbations, and that stabilizes the incredibly noisy vision estimates before they ever even touch the physical robot.
Which is so necessary when you're dealing with internet video. And I want to drop the headline metric right now because it's staggering.
Oh, the success rate jump.
Yeah. This pipeline took, in the wild internet video, retargeting success rates from a baseline of just 25% all the way up to 71%.
And, they deploy these extracted trajectories directly to a real 22 degree of freedom Sherpa wave robotic hand.
Mounted on a UR3E arm, so you have raw, compressed YouTube slop going in and actual physical robotic actuation coming out.
It's honestly incredible.
But getting from a flat 2D screen to a physical 4D map, that's the first massive hurdle, right? Because we know if you just throw standard trackers at a YouTube video, the pipeline usually just shatters immediately.
Right, yeah. Joint hand-object reconstruction models do exist, but historically they always assume clean lab data.
Or like closed object taxonomies, right?
Exactly. But for in the wild video, the authors found that a modular decomposition is just significantly more robust.
So break it down.
Yeah. They use HaWoR, that's HAWOR, hand world reconstruction for tracking the human hand.
Oh, okay, got it.
And then they use SAM3 for segmentation and Moj for depth and camera intrinsics.
But the real bottleneck is the object tracking itself, isn't it?
Oh, absolutely. If you use a standard 6 degree of freedom object tracker like Foundation Pose or any 6D on just raw internet video,
it fails when the hand gets in the way.
Right. The moment the human hand wraps around the object and severely occludes it, the tracker just loses pose lock.
It drifts.
It drifts, and it completely fails to reacquire the object when the hand finally moves away.
Which means your robotic training trajectory just dies right there on frame 12.
Exactly. End of rollout.
So to get around this, they bypass standard trackers entirely, and they hack SAM3D into a continuous video object tracker.
Yeah, which is super clever. Because SAM3D is an image-to-3D generative model. It was originally designed to just build a static mesh from a single image.
Right. And I was honestly a bit lost on how they actually execute this flow matching inference over time. Because, if you have a massive generative backbone, trying to run that frame by frame on a video should completely fry your compute cluster, shouldn't it?
Well, it would if you ran it naively.
Okay, so how do they not fry the cluster?
So SAM3D learns a joint distribution over shape and pose. Normally, running it frame by frame gives you a slightly different 3D mesh every single time.
Right, so you'd have zero temporal coherence.
Exactly, but because shape and pose share the same latent space, the authors fix the shape latent at an anchor frame.
Oh, so they lock it in.
Yeah. From then on, during inference, they only update the pose latent frame by frame.
Okay, I think I get it. It's like, think of it like sculpting clay on a turntable.
That's a good analogy, yeah.
Like, instead of sculpting a new shape from scratch for every single frame of the video, you bake the clay hard at the first frame.
Right, the shape is locked.
And then for the rest of the video, the AI is only allowed to spin and tilt the turntable to update the pose. It can't reshape the clay.
That physical constraint makes total sense for video tracking. But underneath the hood, they are exploiting the flow matching inference itself.
Wait, how so?
Well, they're producing a sample by integrating an ordinary differential equation, an ODE, from pure noise to the data distribution.
Right, standard diffusion stuff.
Yeah. But at each mathematical step, or Euler's step, they take the model's free update for both the shape and pose blocks, and they blend it towards target interpolants.
Oh, so they are constantly nudging the shape back to the canonical baked shape.
Exactly, and nudging the pose toward the previous frame's pose.
Got it. But using a fixed pose guidance parameter might cause over-rigidity, right? Like where the tracker refuses to let the object rotate even when it physically is rotating in the video.
Yeah, or it might cause spurious flips. So to solve this, they extract 2D point tracks using Bootstaper.
Bootstaper, okay.
Yeah.
And that estimates the object's rotational velocity directly from the pixels.
You got it. If the object is spinning rapidly in the video, they dynamically drop the guidance strength.
So the model is allowed to shift the 3D pose more aggressively.
Right. And if it's relatively still, they keep the guidance high to prevent jitter.
That is so smart. And this brings up the sampling challenge because diffusion is inherently a stochastic process.
Yeah, they draw 25 candidate poses per frame.
Okay, let's put this into perspective for anyone trying to build this pipeline. If you want to do this the mathematically pure way, you would rank those 25 candidates by the model's own conditional log density.
Which is computationally insane.
Right. If you have 13 pose dimensions, 25 ODE steps, and 25 candidates, you are looking at roughly 8,700 forward and backward passes through the diffusion backbone.
Computing dense vector Jacobian products.
Just for one frame of video, I mean, that is like trying to brute force a combination lock by pulling out an electron microscope and checking the atomic structure of every single microscopic scratch on the dial.
Yeah, it is totally prohibitive at video scale. The pipeline would grind to an absolute halt.
So what's their workaround?
Instead, the authors use a weighted SE3 distance clustering heuristic.
SC3 clustering. Okay, break that down.
They take the 25 generated samples and compute the translation and geodesic rotational distances between them.
So in plain terms, they just look at how the 3D positions and rotations cluster physically in the SE3 space.
Exactly. They discard the small outlier clusters and rank the dense remaining ones by their 2D silhouette intersection over union against the input mask.
And that avoids the massive compute costs.
It adds virtually zero computational cost over the generation itself.
Okay, but let me play devil's advocate here for a second. Why does that SE3 physical clustering heuristic actually work so well if it completely skips all that rigorous log density math?
That's a great question.
I mean, if the vision model is uncertain because of a blurry YouTube frame, doesn't estimator noise just turn those 25 samples into a random, ruined mess of data?
Well, when the model is confident, the generated samples heavily concentrate on the exact same pose mode. The true signal clusters tightly.
Okay, sure. But what about the noise?
Estimator noise, by its very nature, scatters randomly across the SE3 space. Noise doesn't coordinate.
Oh, so by looking for the densest physical cluster, you naturally isolate the best pose mode.
Exactly. You filter out the noise without ever having to re-invoke the diffusion backbone to calculate the exact log density.
That is incredibly elegant. So we have our vision stack solved. The AI is successfully tracking the human hand and the object through time. But because they were tracked by two completely different foundation models, HaWoR for the hand, SAM3D for the object, they're floating in two totally different virtual spaces.
See? Yeah, they exist in slightly different metric spaces.
So how do we force them into the same reality?
This requires a highly specific depth map alignment, and they utilize the point maps generated by Moog to do it.
Okay, so how does the Moog alignment work?
The pipeline calculates three critical centroids. First is the centroid of the visible portion of the HaWoR hand mesh.
And that acts as the near metric ground truth, right?
Right, then it calculates the centroids for both the hand and the object in the Moog point map space.
So you essentially have a relative map from Moog and an absolute map from HaWoR.
You got it.
Right.
And by dividing the HaWoR hand depth by the Moog hand depth, you get a depth scaling ratio. Let's call it K.
Okay, K, and then what?
To place the object relative to the hand in the true metric space, the system takes the hand-to-object offset from the Moog point map, rescales it by that calculated ratio K, and adds it to the HaWoR hand centroid.
I picture this like threading a needle down the camera's z-axis. Like, you know exactly what the object looks like from SAM3D, and you know its orientation, but you have to slide it back and forth along the line of sight until the depth perfectly matches the hand scale.
That's a perfect way to visualize it. The orientation is held fixed, and the pipeline solves a 1D least squares optimization on a single scalar to adjust the object's translation relative to the camera.
And then I assume, following that translation, they have to align it with gravity.
Yes, the entire trajectory is run through GeoCalib to align it with real-world gravity.
Which is essential, right? Because physical robots operate in a gravity-bound simulator, not a floating, orientationless camera frame.
Oh, absolutely. If gravity is pointing sideways relative to your data because, say, the person filming the YouTube video tilted their phone.
The physics engine will immediately collapse the simulation when you try to retarget the motion.
Yeah, it would be a disaster.
But that reliance on monocular depth brings up a fundamental ambiguity.
The hovering problem.
Yeah. If you are looking through a single camera lens, how does the system distinguish actual physical contact from a visual illusion where the hand is just hovering like 2 inches in front of the object?
It's really tough.
Because if the lighting is weird or the angle is sharp in a video, a 2D image can easily make a hovering hand look like a firm structural grasp.
Right. The vision models are making their best guess based on occlusion and pixel shadows, but they can absolutely be wrong.
Is that addressed in the paper?
Yeah, the paper explicitly lists this as a limitation. You are bound by the geometric constraints of a single viewpoint.
And that visual vulnerability brings us perfectly to the next massive challenge, crossing the actual embodiment gap from human anatomy to robot hardware.
Yeah, because we now have a beautiful 4D movie of a human hand manipulating an object.
But a human hand has soft tissue, specific joint lengths, and unique kinematic constraints.
And the 22 degree of freedom sharp wave robot hand is made of metal and plastic. It has vastly different geometry.
So if you just tell the robot joints to blindly copy the human joints, it's a guaranteed disaster.
100%. Early systems relied heavily on purely kinematic retargeting. They would use an inverse kinematic solver, like in this paper's baseline, they use a tool called MINC.
MINC, right, to try and match the fingertips of the robot directly to the 4D reference trajectory.
But kinematic retargeting is totally blind to physics. It ignores forces. It ignores rigid body collisions.
So if you copy the human trajectory onto metal fingers, the robot fingers will just clip straight through the solid geometry of a coffee mug.
Or they will slide right off the surface because they aren't generating any normal force against the object.
Okay, so the real heavy lifting has to happen in a dynamics-aware retargeting process.
Exactly. They pull the trajectory into MuJoCo warp, running the physics simulation at 200 hertz and planning the control at 2 hertz.
And they utilize an MPPI-style sampling-based optimization.
Right, model predictive path integral. For every single step, they evaluate 124 distinct sample trajectories over 32 iterations.
Just hunting for the physical control inputs that best track the reference while strictly obeying the laws of physics.
Yeah, but dealing with reconstructed internet video means the reference trajectory is inherently noisy.
It's slop.
It's slop. So to make the MPPI optimizers survive this, the authors introduced 3 major innovations.
Okay, what's the first one?
The first, and arguably the most impactful, is the introduction of warm-up steps.
Right, because I was trying to visualize the failure mode without this. If our vision model feeds the simulator a jittery, noisy first frame where the human fingers are mathematically clipping straight through the object, wouldn't the physics engine just violently repel the rigid bodies?
Oh, yeah. The object would shoot across the room like a bullet, and the optimizer would reject the trajectory immediately.
So that phenomenon is exactly what the warm-up steps prevent.
Exactly. If the first frame is a geometric collision, the whole rollout is doomed before it begins. To circumvent this, they prepend a series of warm-up steps where the object is literally welded in midair in the simulator.
Welded in midair. That is wild.
Right, and the robot hand is given time to move freely and pre-adjust to a stable, physically valid grasp around the object before the optimization even attempts to track the human reference motion.
And then once the warm-up is done,
the weld is removed, gravity kicks in, and the tracking begins. It sees countless initial frame estimation errors without relying on hard-coded grasping heuristics.
I mean, just giving the robot a second to grip before dropping the object makes perfect sense. Okay, what's innovation number 2?
Innovation number 2 is random force perturbation.
Which feels like pulling a trick straight out of the sim-to-real reinforcement learning playbook.
It really does. During the rollouts, the system applies random forces and torques to shove the object.
Why do they need to shove it?
Because without this perturbation, the optimizer can easily fall into brittle local minima. For example, the robot might find a bizarre way to balance a heavy object delicately on the very tips of its metal fingers just to satisfy a tracking reward for a few frames.
And in simulation, it looks fine.
But in reality, that grasp would slip instantly due to microvibrations.
Ah, I see. So perturbing the object in simulation forces the MPPI optimizer to discard those fragile solutions.
Exactly. It selects control trajectories that result in robust, deep grasps capable of surviving minor disturbances.
It demands physical stability, not just visual mimicry. I love that. And the third, innovation.
The third is the transition reward. They add a constant penalty for failed step function transitions.
Give me an example.
So, if the video shows the object resting on the table, but the robot in simulation is hovering it a millimeter above the floor, that triggers a penalty.
Or if the video shows it grasp, but the robot isn't making physical contact, penalty.
Right.
But wait, why is that specific penalty necessary? I mean, if the optimizer is already tracking the general motion, shouldn't the basic tracking reward naturally close that 1 millimeter gap?
Well, a standard tracking reward uses a mean squared error loss function, which naturally smooths out physical states. So if the robot's hand is off by 1 centimeter while waving through the air, it's a minor error. But if it's off by 1 centimeter when it's supposed to be picking an object up off a table, it misses the object entirely.
Oh, so the transition reward prevents the optimizer from smoothing over binary physical states.
Exactly. It forces the system to respect the hard boundaries of resting versus in hand, which are absolutely critical for successful multi-stage tasks.
The theory and the pipeline architecture are just beautiful. But, for the ML engineers listening to this, the ultimate question is always, does this actually scale?
Right. What happens in practice?
Yeah, what happens when we feed it raw, unfiltered internet slop? Let's talk about the empirical results.
The empirical numbers are highly compelling. On the pure reconstruction side, the vision stack sets a new state-of-the-art on both the DexYCB and HOI4D benchmark datasets.
So it's outperforming prior joint hand-object reconstruction methods?
Yeah. And on their 150 video in the wild benchmark, human raters prefer DO as IDO's object, tracking over the foundation pose baseline 67% of the time, with 75% unanimous agreement among raters. Standard trackers simply lost the object under motion blur, while this method maintained lock.
And the retargeting success rate is really the ultimate test of the embodiment gap, isn't it?
Well, for sure. On 655 in the wild reconstructed references, their success rate jumps from 25% with a baseline annealed sampling approach all the way to 71%.
And going back to your point about the physics engine exploding on the first frame.
Yeah, the warm-up steps alone contributed a massive 41% jump in that success rate.
That is insane. Did they test it on clean data too?
They did. They tested it on the clean Oking 2 mocap dataset and improved success there from 72% to 81%. So it proves these innovations optimize clean data just as effectively as noisy data.
What really blew my mind, though, was the real-world deployment.
HaWoR tests.
Yeah, they took these trajectories out of simulation and successfully executed 10 complex tasks on the physical UR3E and SharpaWave setup.
And they didn't just pick up a block.
No, they were whisking a bowl, pouring from a bottle, erasing a whiteboard, hammering a nail, and pulling a tape measure.
The tape measure one is wild.
Think about that tape measure task for a second. You have a YouTube video of a human pulling a flexible tape out of a rigid housing. The vision stack isolates the objects, the alignment stack builds the 3D depth, the Mujoko optimizer figures out how to securely grip the tape without slipping.
And then a 22 degree of freedom robotic arm perfectly mimics the pulling motion in the real world.
It is wild. It proves the pipeline is fully operational end to end.
It does, but the authors also include a crucial analysis for the data scaling folks. They call it the human data filtering playbook.
Oh, this might be the most important takeaway for anyone building data sets right now. I mean, we jokingly named this show AI Paper Slop, but the authors literally found a massive, tangible penalty if you don't properly filter your internet data.
Yeah, they analyzed the 100 DOH dataset. They pulled 2,000 10-second clips that had already been pre-filtered specifically for hand-object interactions.
Okay, so these are supposed to be the good clicks.
Right. But out of those 2,000 pre-filtered clips, human review revealed only 187 actually contained meaningful extractable interaction.
What was wrong with the rest?
The interaction was out of frame, obscured by rapid shot transitions, or blocked by the camera angle.
So then what happened when they ran those 187 clips through the pipeline constraints? Like checking for severe camera motion or unavoidable tracking failures.
Only 83 clips survived.
Only 83 out of 2,000 clips.
Yeah.
That is roughly a 4% survival rate for data that was already supposed to be relevant.
And the authors explicitly point out that this implies a 20x penalty in compute and storage if you aren't rigorously pre-processing your internet videos.
So if you are trying to build a scaling law by just blindly scraping YouTube, 96% of your pre-filtered dataset is essentially useless slop for dexterous learning.
It really forces a complete shift in the paradigm. Because if the DO-as-IDO framework proves that robots can successfully harvest dexterous manipulation data from everyday human videos.
Then the bottleneck in robotics research is no longer collecting robot teleoperation data.
Exactly. The bottleneck is entirely about curating and filtering human data.
Which is fascinating because teleoperation is notoriously slow. It's insanely expensive and heavily limited by the human operator's skill with the clunky VR rig or joystick.
Right, so if you can bypass that physical rig entirely and just scrape YouTube, you unlock millions of hours of behavioral data.
But as with any major leap forward, this pipeline isn't magic. We need to talk about the limitations.
Yeah, the most immediate limitation is that it currently assumes rigid objects.
So no squishy stuff.
No squishy stuff. If you try running this pipeline on a video of a human crumpling a piece of paper or squeezing a sponge, the SAM 3D mesh tracking is going to shatter because the object's canonical shape is mutating.
Makes sense. What else?
It also strictly requires semi-accurate metric depth predictions. And most critically, it only reconstructs the hand and the object. Yeah. It completely ignores the rest of the physical scene.
Which means the optimizer has absolutely no idea if there's a wall in the way, or if the object is being placed inside a specific, tightly constrained container, or interacting with a complex hinge.
Exactly. It lacks all environmental constraints.
Plus, as we discussed, MuJoCo only approximates real-world dynamics. That simulation gap places a hard upper bound on how perfectly these generated trajectories will transfer zero shot to a real physical environment.
Yeah. Solving rigid body open space manipulation from internet video is still a monumental first step, but those scene level constraints are the obvious next frontier for this research.
It absolutely is a monumental leap. So what does this all mean for the future of robot learning? If you are listening to this, I want to leave you with a final thought to mull over. If this pipeline scales and the community figures out how to map the surrounding scene context, what happens when we start pointing these models at videos of humans doing non-rigid tasks?
Like folding laundry?
Exactly. Imagine extracting perfect kinematic and dynamic trajectories for folding laundry or kneading dough just by watching an Italian chef on YouTube. Or better yet, what happens when the internet is inevitably filled with videos of humanoid robots and these models start learning from the visual artifacts of other robots?
Oh, wow.
Does the human-to-robot embodiment gap disappear entirely, or do we just enter an infinite loop of robots training on synthetic robot slop? Go build on this DO-as-IDO framework, test the limits of your own data sets, and let's find out. Catch you on the next one.